I will be presenting on the topic recursive ZKP and trade-off. My name is Yutaka Hashimoto, and I'm ZKP developer at INTMAX. In this presentation, I will explain recursive ZKP, which is a technology which is essential technology from the perspective of client-side validation used in Plasma. So first, let's explain what client-side validation is. So client-side validation was introduced by Dan Robinson's Ethereum research post titled Plasma with Client Validation. This was later refined Vitalik Buten's Plasma Cache. The basic idea is to minimize the burden on base layer as much as possible and do what can be done on the client side. The verification that UTXO has not been double spent is done on client side, not on the base layer. And it is the sender's responsibility to prove to the recipient that UTXO has not been double spent. Recent stateless technologies such as INTMAX and ZK coins are based on client-side validation. So to show that UTXO has not been double spent, we need to prove that UTXO has not been included in blocks before being spent. If T blocks have passed since a UTXO was issued, a direct method would require T exclusion proofs. The amount of data for this exclusion proof increases rapidly and it's quickly unmanageable. And so recursive ZKP solves this problem. So what is recursive ZKP? Ordinary ZKP is a cryptographic tool to show that the statement is true without revealing any information other than statement hold. So, for example, let's take example Fibonacci sequence. So, verifier can verify the 100th term of Fibonacci sequence start with 218 without directly calculating the Fibonacci sequence. So instead of using a ZKP to prove statement about Fibonacci sequence, we can also prove the correctness of ZKP that proves statement about Fibonacci sequence. In other words, this means proving the correctness of ZKP inside a ZKP. This is called a recursive ZKP. This ZKP can be repeatedly any number of times, and by the final verifier checking only the last ZKP, the correctness of initial statement is verified recursively. Let's return to client-side validation. UTXOs are accompanied by a ZKP that proving their history is correct. When consuming a UTXO and to create a new UTXO, we first need to verify that the old ZKP proof is correct and verify that old UTXO has a sufficient amount to create the new UTXO. So recipient create a new ZKP that proves two points. So this is a recursive ZKP. So we call this proof a balance proof. Balance proof is a recursive proof. Every time a participant makes a transfer, the balance proof is updated. And this chain of recursive proof continues until the assets were withdrawn. And there is another important application of recursive ZKP in client-side validation. The right client ZKP. In balance proofs, there are cases where we need to prove that a TX included in plasma blocks. For this, we need to create a Merkle tree of plasma block hashes. Also, in cases like INTMAX, where plasma block verification isn't done on chain, we need to determine whether each block is correct or incorrect inside ZKP. So let's call this ZKP related to plasma blocks a right client ZKP. This is a recursive proof because it needs to be updated every time a new plasma block is posted. So next, I will explain various schemes for performing recursive ZKP. Recursive ZKP scheme can be broadly divided in accumulation scheme and fully recursive ZKPs. Haro and Nova and Protostar belong to accumulation scheme, and recursive stack and recursive growth 16 are examples of fully recursive ZKP. Let me explain the accumulation scheme. Suppose we are given function f and initial value z0. Let's say that after applying f 3 times, we get z3. To prove this, we need to prove 3 statements true. So f of z0 equals to z1, and f of z1 equals to z2, and f of z2 equals to z3. To prove these 3 statements, in normal ZKP, we would need to create 3 ZKP for each statement. In the accumulation scheme, by introducing accumulator, it is possible to accumulate statement into the accumulator. So by verifying the final accumulator is correct, it can be guaranteed that all statements are correct. However, this alone is not sufficient. It is also necessary to verify the process of updating the accumulator is correct. When all verification passes, including accumulator verifier and decider, which verifies the final accumulator, it can be guaranteed that all statements are correct. So in this way, by using accumulators, verification of statement can be transformed into the problem of verification of accumulator. However, the number of accumulator verifier still need to be n times, which is still inefficient. So we include accumulator verifier of each step in the statement of next ZKP. And we fault the accumulator verifier itself. By dividing in this way, only last accumulator verifier is needed. So Haro and Haro2 uses inner product argument as the accumulator. So next, let's explain the folding scheme. All statements can be written as constraint in the form of R1CS. Here, A, B, and C are matrices. And Z is a vector consisting of public input X and 1, which is represent a constant term of the constraint, and W, which is the private input, that is witness. Reduced R1CS is a R1CS that add extra scalar U and error vector E to this R1CS. Reduced R1CS can be used as an accumulator. Let's see this next. So Now suppose we have a relaxed R1CS and another R1CS. And let's consider taking a random linear combination with two R1CS instances. So let's call this random value rho. So we can create new Z by combining Z1 and Z2 by rho. And in this way, by adding extra term U and E, we can absorb the cross terms and result become also R1CS, relaxed R1CS. We call this operation folding. So using relaxed R1CS as accumulator, this becomes Nova's folding. In this way, Nova realizes the accumulation scheme by expressing statement as R1CS and folding them into a relaxed R1CS. Nova's recursive proof is extremely fast and running about 50 milliseconds per step for small circuit. So as a latest result on Nova to client-side validation, we have hypernova and cycle fold. Hypernova enables the folding multiple instances. Also, cycle fold simplified previously complex instantiation of Nova on cycle of elliptic curves. These two achievements made recursive proof of tree structure possible. This allows, for example, merging multiple UTXO into a single UTXO. However, there are also drawbacks when applying accumulation scheme to client-side validation. In accumulation schemes, the nudge property is only guaranteed in the final step. This means that in each step, the verifier can see the somewhat guess the witness the previous prover used. Therefore, the proof is not suitable for privacy payment purpose. Also, when verifying accumulator, the decider needs to verify all types of statements. Therefore, if the recursive structure becomes too complex, the decider becomes too large. For example, in client-side validation, balance proof needs to absorb a right client proof to synchronize the latest plasma block, or merge balance proofs into one to receive funds. In this case, decider needs to verify 4 types of recursive structures. In such situation, the decider becomes too costly. So next, let's look at fully recursive ZKP. Fully recursive ZKP verifies ZKP completely at each step without using accumulators. Although it completely verifies ZKP, stack-based Plonky2, for example, has very good benchmarks. It completes proof less than 500 milliseconds for non-ZK config and less than 2 seconds for ZK config. On the other hand, there is also research on performing a recursive ZKP on gross 16 circuit. This approach requires verifiers of operations on elliptic curve. So this involves non-native field arithmetic, which is result relatively long time of about 200 seconds. So in this presentation, we will take a closer look at stack-based recursive ZKP. Stacks are based on Merkle tree and Reed-Solomon encoding. The bottleneck in prover side is a FFT for Reed-Solomon encoding and hash calculations of constructing Merkle tree. On the other hand, most computationally intensive part of verifier is a verification of hash calculations for verifying Merkle proof. Recursive stack doesn't use elliptic curve, so non-native field arithmetic is not necessary. Also, while most costly part is hash calculation, we can reduce this cost by using ZK-friendly hashes like Poseidon hash. Furthermore, it is possible to further reduce the cost of Poseidon hash verification by using custom gate or ARI specialized for Poseidon hash verification. For example, in Plonky 2, a custom gate with 135 columns is used to verify Poseidon hash. This custom gate allows to verify a Poseidon hash in a single row, enabling fast recursive proofs. However, stack-based proof sizes are very large, ranging from 100 kilobytes to several megabytes. This can be burdened in places with limited communication resources. Also, unlike accumulation schemes, it completely verifies proof at each step. So the cost of verifying ZKP is larger compared to accumulation scheme. So another problem is that after Fiat-Shamir transformation, the security of FRI is difficult to evaluate, and in most cases, we have to use the conjecture security level. So this is the summary. So recursive ZKP plays a crucial role in client-side validation. And accumulation scheme and recursive stacks are promising candidates for recursive proof in client-side validation. However, each has its trade-off. So accumulation scheme can execute a recursive proof extremely quickly, taking about 50 milliseconds. However, there is no zk-ness at each step. Additionally, if the recursive structure is too complex, the cost of decider can become too costly. On the other hand, recursive stack fully verify ZKP at each step. So they don't require decider and can be guaranteed zk-ness at each step. However, the proof size might be large and speed is slower than the accumulation scheme. Nevertheless, by utilizing custom gates such as Poseidon hash, recursion can be achieved at practical speed. Yes, that's all.